Good evening, everyone. So, the final speaker of the day, Professor Kaneenika Sinha, is here with us. The title of the talk today is Counting the Divisors of an Integer. Professor Kaneenika is a faculty in the Department of Mathematics at Indian Institute of Science Education and Research, Pune. Her research interests mainly lie in the intersection of number theory and probability in the context of modular forms, elliptic curves, and regular graphs. Let's welcome her again. Over to Professor Kaneenika.
Thank you. So it's lovely to meet all of you. Thank you for attending the talk. I hope you've been having a good summer school and learning a lot of maths. I saw on your summer school webpage that you have a course going on in curve sketching and you're learning and practicing things related to calculus. So let us just start with some fun things there and then related to things that we do in number theory. Okay. So in calculus, the objects of your interest are functions from S to R, where S is any subset of R. So it could be an interval, it could be non-negative real numbers, it could be all of R, right? So for example, one of the easiest functions to sketch is f of x equal to x. Okay, some other functions that are of interest to us, f of x equal to x to the half, and let us stick to the non-negative real numbers. Okay, and here's a function which is extremely important for people in number theory, and that is logarithm of x. Okay, so if you wanted to plot these functions, right? So y equal to x, so I'm going to just plot them on the non-negative side of the real axis. So this is y equal to x. Let's say this is your 1, okay? What does y equal to x to the half look like? Between 0 and 1, it will grow faster, and then it will go below. Okay, and what about logarithm? Are you familiar with the graph of the logarithm? Yeah, so it starts to be positive from 1, and it grows really slowly, but it keeps growing. Right, and beyond 1, of course, it takes, before 1, it takes negative values. So as you will see here, okay, and here let me just start from x greater than or equal to 1. So the logarithm function grows much slowly as compared to x to the half. And in fact, there's nothing special about x to the half. If you were to take x to the 1/3, x to the 1/4, x to the 1 over 10,000, or x to the 1 over any natural number, or any big positive real number, log of x will eventually be much, much smaller than that function. Okay, so if we talk about functions having growth similar to log x, that is considered a very, very controlled, well-behaved function. And another function that people in number theory play a lot with is the function, and I will leave it as an exercise for you to think about the graph of this function. This is log of log x. Okay, and you can start with the x to be greater than or equal to e. Okay, so it starts to be non-negative from there. Okay, and in general, people in number theory are interested in log x, log x, log x, and lots of logs and logs of x, okay, nested logs. So, and today I'll tell you about some nice functions whose behavior is explained very nicely in terms of functions of these forms. All right. So another nice function that we often see is g of x equal to 1 over x. Okay. So I think you would be familiar with the graph of this function, right? And so what you can do is, so graph would be something like this. So as x increases, 1 over x becomes very, very small. And what I want to do is, I want to understand the sums in terms of the corresponding integral of the function 1 by x. Okay, so are you people familiar with the integral test? How many of you are familiar with the integral test? It's okay if you've forgotten. We'll review it with this particular example. Okay, so let's say this is your 1, 2, 3, and you are going all the way till some natural number n. Okay, now let me draw rectangles as follows. The length here is, this is not the most representative diagram, but you know what is happening. So length of this rectangle is just 1. And what is, the breadth is 1. And what is the length? Because you are taking the function 1 by x, it's just 1 by 2, right? So area of this rectangle would be 1 by 2. Area of this rectangle would be 1 by 3, okay? And all the way till n, okay, what will you have? Okay, so if you take the sum of the areas of all of these rectangles, you have 1 by 2 plus 1 by 3 all the way till 1 over, okay. So we'll take 1 over n, okay. And if you were trying to understand the area of this curve from 1 to n, what would you have? You would have the function 1 by x dx integrated from y0 starting from 1, okay, 1 to n. So which of these do you think should be greater? The integral should be greater because the rectangles are smaller when you, right? When you take all the rectangles, visually you can see that the area is smaller. So you have this. Now we would like to start our sum from 1. Okay, so there is 1 missing. You've started from half. So if I added 1 here, what would happen? I would add a 1 here as well. Okay, and what is this integral? Log n, right? So this is 1 plus log n. Now you can do the same thing for rectangles whose areas will exceed the area under this curve. If you started off with the rectangle whose length is f of 1 and breadth is 1, okay, you know this is going beyond our integral. So it turns out that 1 plus a half plus 1/3 plus 1 over n minus 1, this should be greater than or equal to, okay, now what would be the corresponding integral here? Same, right? 1 to n, 1 by x dx is equal to log n, okay? And now if I add 1 by n to this, I will need to add 1 by n to this side as well, okay? So what we have is, we are expressing the area under area of this function from 1 to n We are bounding it below and above, okay? And so we've got this inequality, 1 over n plus log n is less than or equal to summation n going from 1 to capital N, 1 over n, and it is bounded above by 1 plus log n. Okay? And one other thing we observe from here is, if you take the difference, n going from 1 to n, 1 over n minus log n, what happens to this? This is bounded above by 1 and bounded below by 1 by capital N for any positive integer n. So what happens as capital N goes to infinity? This is holding true for every n. So clearly, as n goes to infinity, this will lie between 0 and 1. But we know something even stronger. Suppose I consider this as a sequence and I give it a name. Gamma sub n is equal to this particular difference. It turns out to be a monotonically decreasing sequence. Okay, I leave it as an exercise for you to verify that this is a monotonically decreasing sequence which is bounded. So what do you know about such sequences? They converge. Okay, so we give the limit a name, and this is known as Euler's constant, an object of great interest in mathematics and particularly to number theorists. And this particular object will come in handy for us in the study of many important concepts in number theory. And if you want to know what the value is, approximately it is 0.5, I believe, up to the first 5 decimal places. Okay, so it's greater than half. Okay. Now, in number theory, our interest is with functions which are defined on the set of natural numbers. Okay? And sometimes they may take natural numbers itself. The range is also in the set of natural numbers. So the kind of functions that I want to discuss with you today, and I hope you will have fun thinking about this function, is the following. So given a natural number n, let d of n denote the number of positive divisors of n. Okay? And let me also introduce a related function which I call omega of n. Here I restrict my attention to the number of prime divisors of n. Okay? So this is the Now, what can you say about the relationship between the two? It is clear that omega of n would be less than or equal to d of n. So let us just stare at these functions and let's write down the values for some bunch of numbers. So n is equal to 1. So this is not very interesting, but it has one positive divisor itself. And what is omega of n? It's just 0. Let us take n to be equal to 2. The number of positive divisors here is 1, and so the 2 divisors are, okay. And what is omega of n? We are just 1, right? And there is nothing special about 2 right here, what if I took n to be any prime number? You know that the number of positive divisors of a prime number is 2 and omega of n is equal to 1, right? Suppose you had a number of the form n equal to p times q. How many divisors would this have? Positive divisors. 1, p, q and pq, right? So basically any divisor of n is either it will have q as a factor or it will not have q as a factor. Either it will have p as a factor or it will not have p as a factor, right? So the total number of divisors here is 4 and the number of distinct divisors is 2. Now suppose I were to take p square q. What would happen here? Omega of n will not change because it is the number of distinct prime divisors. So p will get counted only once, even though you have it in a higher power, right? So omega of n is 2. What happens to d of n now? Why is that so? So the factors of p square that can show up are 1, p square, and the factors of q, 1 or q, right? So 2 into 3, that is 6. Similarly, if I were to take p raised to the a, q raised to the b, where p and q are distinct primes, okay, omega of n will still remain the same. It will be 2. But now what about d of n? Excellent. A plus 1 into b plus 1. So depending on the exponent, this value will change. Now, one of the things that we have learned, perhaps you would have learned it in school or later, is that any natural number can be written as a product of prime numbers, and it can be done uniquely, right? So this representation of n helps us to study many nice functions in number theory. So suppose I take p1 to the a1, p2 to the a2, all the way till p sub k raised to the a sub k, where all the ai's are at least 1, right? Continuing the patterns that we have been learning, what can you tell me about d of n? How many? Yeah? Right. Product of a1 plus 1, a2 plus 1, and all the way till. And what is omega? It's just k, right? Okay. You can also make another observation, which is that 2 raised to the omega of n, okay, this is less than or equal to. So what I'm doing is, since each prime is at least 2, right? So each prime power is also at least 2, right? So 2 into 2 into 2, k many times, is less than or equal to n itself. And this immediately tells us that omega of n is a well-behaved function in terms of its upper bounds. Okay. D of n is not as nice, but you can also say a lot of nice things about d of n. One thing you can immediately say about d of n is, suppose you write n to be equal to a times b. At least one of them has to be less than or equal to root n. Because if both were greater than root n, they cannot multiply to be n, right? So this tells you that if you wanted to count d of n At most, this fact that at least one of the factors should be less than or equal to root n. Okay, what this is telling you is that d of n is less than or equal to 2 times root n. Okay, so this is a slightly more non-trivial bound as compared to just saying d of n is less than or equal to n or some such thing. And I will let you think about the comparison of d of n with say n to the 1/3. There the reasoning will change due to lack of time. I won't go so much into this. You can derive a positive constant such that d of n would be bounded above by c times n to the 1/3. And this is an absolute constant. So even though it may not be 1, it may be something different. What this is telling you is that irrespective of what n you take, this remains the same. So this type of an inequality is also giving you useful information about how d of n grows. And there is nothing special about 1/3. You can actually replace this by any small positive number. Okay, so for any positive epsilon, you can find an absolute constant c such that d of n is less than or equal to c times n to the epsilon. So it is better than, it is smaller than a constant times n to the half, n to the 1/3, n to the 1 over 1 million, anything like that. Okay. However, omega of n is even nicer because omega of n is bounded above by a constant times log n. And why is that? Why does that make omega of n better controlled? Here is another small calculus exercise for you. I hope you will think about it and we can discuss it during the question session as well. For any real number x greater than or equal to 1, you can show that. So let x be greater than or equal to 1. You can show that log of x is bounded above by x to the a times an absolute constant that depends on a. Okay, and this holds for any a. So you can make it very, very small. So what this is telling you is that log x, the growth of log x is smaller as compared to any power of x. This is an important toolkit for number theorists. Right? And if from log x, if we go to log x, that would be even better. Right? So in this, we will explore the growth of some of our number theoretic functions, especially these two functions, in the context of what calculus tells us about function of the form log x or x raised to the some arbitrary small power. Right? Okay. Any questions so far? All okay? Now, one thing you will notice is that these functions don't seem to follow a specific type of a pattern. You could have a prime number, but the number before it could be a highly composite number, or the number after it could also be a very highly composite number. Okay? So there is no, maybe for your own, to have some fun, take some 3-digit numbers, for example, a string of 3-digit numbers, and see how d of n and even omega of n would seem to fluctuate a lot between these values. So if you are trying to understand the behavior of this function, you ask a slightly different question. What you do is, you take the set a to be equal to all the natural numbers up till capital N and explore what happens to your d of n and omega of n on average as you vary your number between 1 and capital N. Yeah? Oh, so all I'm saying is, so suppose you were to take the set S1 to be equal to all the, let's say, all the natural numbers which are less than or equal to root n. Okay, let's say S2 is the same, but I index this by, okay. What does D of n measure? So if you have any number, as we saw, it can be written as a product of two numbers, at least one of which is less than or equal to root n. So corresponding, if you're trying to evaluate D of n, you can actually try and evaluate all possible two tuples A comma B such that their product is n, right? And the number of such tuples would definitely be less than or equal to the cardinality of S1 plus cardinality of S2. Okay, so this is the reason. But when you go to n to the 1/3, this type of reasoning will not go directly. You have to think of some more fun things there. So I'll leave that as an exercise for you to think about. All right. So, yeah. So let us look at this set. And what are we trying to do? Let's evaluate D of n as n runs from 1 to capital N. Okay, so if the function is not behaving very smoothly at specific values or seems to oscillate a lot, ask what happens to the function on average. All right, so you have this. So you write n going from 1 to n, but what is D of n doing? It assigns, it's counting the number of positive divisors. So basically it's a function that is assigning the weight 1 for every positive divisor of n, right? So each time D, so I'm going to use this notation, D dividing n. Okay, this notation means n is a multiple of D. So for every n running from 1 to capital N, I need to know how many divisors it has. So take the sum over all the divisors and put 1 to this sum. Is this clear? Okay, so now we've got this nice sum, but whenever you don't see a direct way of proceeding with a sum, what you can do is you can rearrange your sum in a form that looks more natural. Unfortunately for us here, rearrangement is direct because you don't even have to worry about convergence. These are all finite sums. Okay, so if I were to say that instead of first taking all the natural numbers and then running over each divisor, I change the game. I first go over all the numbers running from 1 to capital N, and for each D, I take all multiples which are less than or equal to capital N. All right. So take all the E such that, and all the E natural numbers, so that DE is less than or equal to. So this is a rearrangement of the sums of the divisor function that we are looking at. Now what happens? I still keep D going from 1 to N, but what is happening over here? You are running over all the E's such that E is less than or equal to capital N over D. That's your inner sum, right? So how many natural numbers can you have less than or equal to N over D? Is there a function that describes this quantity? N over D need not be an integer, right? The greatest integer function, very good. So you have N over D, right? Okay. Now, how is this greatest integer related to the function N over D? If you remove the greatest integer, what happens? So I write the greatest integer any x can be written as its greatest integer plus something that remains, and what do you call it? The fractional part of x. And what do you know about the fractional part of x? It has to be less than 1, lies between 0 and 1, right? So I do the same thing here, and I go from 1 to capital N, right? And I write n over d minus the fractional part of n over d. Right? So this sum is d going from 1 to n, right? N times 1 over d, and in fact you can even bring n out and just keep 1 over d. We spent a few minutes looking at this sum, right, and relating it to the logarithmic function. Okay, what happens to this part? Now here, I'm not really after a precise value. All I do is I observe that because of the fact that this number lies between 0 and 1, the growth of this thing would be much smaller than this particular part of the sum, which we call the main term because we have a precise value for it. What is important for us to evaluate or to analyze this remaining part is to just observe that each of these has absolute value bounded above by 1. And how many terms are there? N, at most n. So what I say is, this thing, we use this symbol, which is the big O notation. All that this notation means is that the difference between the thing that you have started off with and this particular main term, which is a very exact formula, is at most some constant times n, right? Why is this helpful? So remember, we saw that this particular sum is actually very, very close to log of n, right? That was one of the first few things we learned today. So that can be made a little more precise in terms of the Euler's constant that we saw. So you can actually write this as log n, okay, with a little more thought. This turns out to be equal to log n plus Euler's constant plus something which is very small, which decays along with n, and we also know the order in which it decays. So again, I use this word O, this notation O of 1 by n. I know I have not formally defined it, but what it really means is that it is at most some constant times 1 by n. So you have this, okay? Plus you also have another error term waiting for you, which is O of n, right? And when you club this together, what do you get? You get n log n, right, plus gamma times n. So some constant times n, but you already have another error term which is also measuring that dependence on n, right? So what this turns out to be equal to is, this is n log n plus O of n. Whatever this is not a precise value, but whatever this is, it does not grow faster than capital N. So n log n is the dominant contribution when you are looking at this particular sum here. Right? So a short summary of what we have learned so far. You have a function that is taking values which are natural numbers, and you are trying to sum this up from 1 to capital N. And you also have another function which is of a very different nature. The greatest integer function. Okay, greatest integer individually d of n may not be equal to the greatest integer of capital N over N. But as you sum from 1 to capital N, these two match exactly. The sums of these two match. Okay, so I hope you will reflect a little bit on this equality. The main thing is that d of n and greatest integer of capital N over N are two very different functions. But when you sum them up over a bunch of integers, you seem to get the same value. So on average, they behave like each other. And then using the fact that this can be written as capital N over little n plus an error term which does not grow as fast as the main term, you will end up getting that this is n log n plus an error contribution which won't be too bad. N log n will still dominate our sum. All right? Okay. How am I doing with time? Okay. Now let's go to omega of n. Right? So again I take n going from 1 to capital N, omega of n. I can carry on in the same manner as what I did with sum of d of n, but what will be the difference here? We are only summing the prime divisors of n. So I first write n going from 1 to capital N, and my second sum is over the divisors, but those divisors which are primes. P divides n. Now you can repeat the same thing that you did for the previous function, and what do you get? If you do the interchange or the rearrangement as you did for the previous case, what will you have? The first sum running over P is 1, 2. So all the primes, I'll denote P to be primes. Okay, all the primes P less than or equal to n, P prime. And what will the inner sum be? It will be running over all the e's, all the positive integers e, such that P times e is less than or equal to n. Right? So in the top sum, first you went over each integer from 1 to capital N, and for each of these integers you counted the number of prime divisors. And how do you rearrange it? First you go over all the primes up to capital N and consider all possible multiples which are also bounded above by capital N. So in form this is very similar to the previous function, but what do you have? P prime. Okay. What will this sum be? Just follow the same principle that you followed in the last one. This is the greatest integer of n over p. But now you are only running over primes up to n, right? And if you were to simplify this as you did it for d of n, you will again get all primes up to n, capital N over p, right? So you can bring n outside and you have sums of the reciprocals of primes up to n. Now we are entering into very, very important territory for number theorists. Now you have sums over prime numbers, right? Plus O of n. It is at most n. It's actually O of the number of primes up to n, which is, for now, it's okay for us to just write that as O of n, because this particular function now will behave like a function which is related to the logarithm. So let us look at this particular. Right? Now we were talking about the fundamental theorem of arithmetic, which tells us that any natural number can be uniquely written as a product of prime numbers, right? Suppose I take the following product here, p less than or equal to n, and corresponding to each prime p, I take the following geometric sum, 1 over 1 by p plus 1 over p squared, and so on. Okay? And on the left hand side, I write just 1 over n, the function that we have, which we have already studied in detail, right, and related to the logarithmic function. What do you think should be the relationship between the two quantities here? If n is less than or equal to capital N, and you were to write n in terms of its prime powers, what can you say about each of the prime powers? We wrote this here, right? N is equal to this prime number decomposition. N is at most capital N. What can you tell me about each of these prime powers? Just give me the simplest answer. Greater than or equal to 1 and less than or equal to? Each of these will also be at most n, right? Even maybe smaller, but definitely at most n, right? So what am I doing on the right hand side over here? I'm taking all the primes up to n, right? But I have these infinite sums corresponding, but if I were to multiply this for each prime factor up to n, what kind of terms would you get? If I were to take each prime p up to capital N, right, I would have, yeah? Right. And more, right? Exactly. So what Ahona is suggesting is, so each number of the following form, pk to the a sub k, where pk's are at most n, will show up as a term in this infinite product, right? So each of the terms here, little n, will show up somewhere in this product. So we have this inequality. Okay. One other thing. What is this infinite sum? This you will know, right? It's a geometric progression. And what is the value? 1 over 1 minus 1 by p. So you have 1 minus 1 over p inverse. Okay? Okay. So now what I do is I take the logarithms of both sides. Log of n less than or equal to capital N, 1 over n. Okay? This is less than or equal to. Now if you take the log of a product, what happens? It just changes into the sum of the logs, and then there is a negative. So sum of primes p up to n, log of 1 minus 1 over p. Now do you remember the series expansion of log of 1 minus 1 over p, the Taylor series expansion, or have you seen your logarithmic function? Log of 1 minus x, where x is of absolute value less than 1. also has an expansion as an infinite series, which is, so let me first write the left hand side, n, yeah, 1 over n is less than or equal to, yeah, so all the, yeah, go ahead. 1 by p cube.
And plus 1 by
P cube. So p square doesn't show up. Minus log of 1 minus x is x plus x cube by 3 plus x to the 5 by 5. But that's okay. What it does tell you is that this is equal to 1 over p, okay, plus again something which is of a much smaller order, right? I don't care so much about the constants. I'm just trying to understand how it grows in comparison with this thing here. So I have, so the quantity that we are after is this particular sum, okay? This is greater than or equal to log of something which we have already seen, right? What was this quantity? It was log n plus some constant plus something very, very small, right? So if you isolate the parts of both sides for which you have precise information and parts which you don't know precisely but which you understand grows in a certain way, and you club this together, what you end up getting is that your p greater than or equal to n, sorry, less than or equal to n, 1 over p, turns out to be at least log of the main term here, which was log of n. So now you see you have log of capital N, okay, plus some constant, some positive constant. So whatever this sum is, 1 over p, its growth is at least of the order of log n, okay? And this is why when you put all of this information back into the sum over here, okay, and add some more precise considerations, what you end up getting is the following. Summation of n up to n of omega of n turns out to be equal to n times log n plus O of n. Okay, log n times log n will definitely grow faster than n. So I don't care so much about what constant is showing up here. And what did you have for d of n on average, or rather as you sum from 1 to capital N, you had n times log n plus O of n. Which do you think is growing faster? So even when you consider sums, this, which you, in a way you already knew that d of n is greater than or equal to omega of n for each n. But these two formulas are also showing you on average how does one grow in comparison to the other, right? So in number theory, we address a lot of questions pertaining to growth of interesting number theoretic functions, and we try to express them in terms of functions that you understand from your calculus. And the techniques that I showed you so far are fairly elementary techniques, but if you want to make your understanding more and more refined, you have to go back to your techniques and refine them right? If you do the same thing over and over again, you'll get the same answers. So if you want something better, you have to inject some new information, which is where you start putting or you start using more refined techniques from analysis. And that is what is called analytic number theory. A lot of these functions that we are interested in are eventually expressed in terms of behavior of prime numbers. So here, how did that aspect reflect? We were interested in the sums of reciprocals of primes, right? One other interesting consequence of what we wrote down here is that there have to be infinitely many primes. Why is that so? You have this inequality here. As capital N goes to infinity, you know that the right hand side is going to infinity, right? So the left hand side also has to go to infinity as capital N goes to infinity. What does that mean? Yeah, exactly. If there were only finitely many primes, the left hand side would be a finite sum which is greater than or equal to something which is going to infinity. That cannot happen. So this is an analytic way of looking at the fact that there are infinitely many primes. You would have seen other proofs of this fact, right? You saw, suppose there were only finitely many primes, you took their product, added 1 to it, and this gave you another prime which would have to be different from any of the primes. But this is an analytic and a slightly more refined way of saying the same thing. Not only is it telling you that there are infinitely many primes, it is also telling you how this reciprocal, the sum of these reciprocals, grows in terms of this quantity capital N. Okay, so it is making the infinitude of primes effective. Okay, all right. So now coming back to our reflections on these functions and other types of functions in number theory. As I said, if you want better information, you have to start putting down more refined techniques. And this takes us into several nice streams in this subject. You have a question? Yeah? It is some positive constant. Yes, I don't know the precise value, but it is some positive constant, right? Which will not depend on capital N. So as N keeps growing, that constant will remain the same, whereas the functions that depend on N will keep growing. So that is the significance, all right? Yeah. Yeah, it's just the sharpest information available to us because log of 1 minus 1 by x, this thing is, what is this? So what is each of these terms? 1 by p plus 1 over 3p cube and so on. So yeah, you could write something weaker, but if we have something stronger, why not? Right? Is your objection that I'm writing something weaker? No, right? Because sums of, by the way, what happens to sums of 1 over p cube? Do they converge or diverge? They will converge. Why? Summation 1, yeah, sorry, go ahead. Yeah. Yeah. That's right. And can you do the direct thing just by saying that sum over 1 over p cube is just sum of 1 over n cube, right? You know that converges. We don't know the particular value, right? But that also converges. So it's the same argument. You can just do it for 3, right? So basically, whatever information you have here, you can condense it into this inequality, right? Do you think you would have got something better than this, like C1 over N? Was that your question? We can discuss this during the question session if there is a chance of getting better bounds. Okay? Okay. Let me ask you one more question. Actually, let me discuss a couple of more things about these functions, just to tell you about how their behavior is different from each other, even though both are actually picking up from divisors of an integer. So you told me that if n is equal to p1 raised to the a1, p2 raised to the a2 up till p sub k raised to the a sub k, then d of n is this function depending on the exponents. Okay. Suppose you had two numbers n and m such that the GCD of n and m is equal to 1. So if you wrote down their prime factorizations, the prime numbers that show up in each would be different. There would be no match between the prime factors for n or m. So in this case, it will turn out that d of the product of n and m will turn out to be equal to d of n times d of m. Okay. For example, if you had n is equal to p and m is equal to q square, right? You told me that d of p q square is 6, which is 2 into 3, which is d of p into d of q square. You can generalize the same argument for other types of combinations of prime powers. What about omega? Omega is only counting the number of distinct prime divisors. So in this case, omega of n is just counting k. We don't care what the exponents are, right? So if you were to take two different numbers with their prime factorization where the prime factors don't intersect, what will happen when you take the product of, think for example, omega of p square q. What is this? This is just 2. What is omega of p square? 1. Omega of q is also 1. So it will turn out that omega of n times m will be equal to omega of n plus omega of m if the GCD of n and m is equal to 1. So in mathematical parlance, these are called multiplicative functions. D of n is a multiplicative function. It respects multiplicativity, whereas omega of n is an additive function. Okay, and the way you analyze multiplicative, I'm just about to finish. The way you analyze multiplicative and additive functions are very, very different. So we are running out of time. I just want to give you a brief glimpse of things. And I hope you will go ahead and explore this more. Suppose I were to take a multiplicative, any multiplicative function, but in particular, d of n. What we often do in number theory is put functions of our choice into generating series of this form. Okay, where S is, say, just ensure that this is an absolutely convergent series. Okay. Now, because of the fact that d of n can be reduced into d of its prime powers because of multiplicativity, you can actually write, following the same argument that we saw before, you can write this as product over primes, okay? 1 plus d of p over p to the s plus d of p square over p to the 2s and so on. And I leave it as an exercise for you to figure out, because you know the values of each of these. This will just turn out to be product over p, 1 minus 1 by p raised to the s raised to the minus. Please note this down and work this out. You'll really enjoy this exercise. So in analytic number theory, whenever we see a multiplicative function, we put them into series of this form, write them down as products coming from the prime factors, and these are called Euler product factorizations. Euler is everywhere, right? And then we have to start using analytic properties of functions of this form to derive information about the individual quantities of D of n or averages as we need. You, however, cannot do this with additive functions. So additive functions take you to a different domain of number theory where you bring in different types of techniques to address those. So I'm running out of time, so I'll stop on this note and we can discuss more later.
Thank you, ma'am, for such an amazing talk. I think now we are ready to take questions from the audience.
Yeah. S is any number, any positive number, which, any real number which will ensure that this sum converges. So I think I should have written down that n runs from 1 to infinity. For example, you can actually take n square. If S feels too abstract, try with S equal to 2 and see that you will end up getting. And then go back to the method and see you will be able to generalize this to a lot of positive numbers S. More generally, we can also take S to be complex numbers, where the real part of that complex number is large enough. And in fact, it becomes essential to convert our study to these complex analytic functions to be able to derive nice information about sums of this form. That's basically the analysis in analytic number theory. In your third year onwards, you will start studying complex analysis, then you'll understand these techniques better.
Any more questions? Okay. So let us thank the speaker once again.